Good morning, one and all. This is Sainath Reddy Kangidi. Today I am here by to give a presentation, to give my final presentation on active flow control over airfoil using synthetic jet actuators. So, firstly, so mm, during this in this presentation, I gonna explain abstract, introduction, literature review, problem definition, objectives, methodology, results in very easy manner. So let's dive into it. So firstly, abstract. So my project primarily focus on studying the boundary layer separation. So firstly, boundary layer separation is defined as a process where beyond the certain limit, if the airfoil, if the wing of an aircraft, uh, if the angle of attack of the airfoil increase beyond a certain point, as a result, the lift is to drag ratio gonna reduce, which may cause the boundary layer separation. So these boundary layer separation which reduce aerodynamic performance. So in order to tackle this, there gonna be two processes. One is passive and active, which we're gonna discuss later. So out of those, we're gonna choose active flow control. Why? Because from my literature review, I came to know this active flow controls, also known as energy source. So these active flow controls can typically applied in field of aerospace. Why? Because these active controls can significantly reduce skin friction drag and allow pilots to control actuators when needed, whereas in the passive we can't control them. First, introduction. First, dynamic stall, also known as boundary separation, is a phenomena which occurs when an aircraft experiences a rapid change of angle of attack, which results in sudden increase in lift force. These can be caused by maneuvers such as quick turns or stalls, and can lead to increased drag and reduced lift. Why? Because in the field of aviation, the lift is to drag ratio is the important factor. So due to this boundary separation, the performance gonna reduce and it increases the drag, which proportionally decrease the lift. So for this, they're gonna be passive, they're gonna be active. In passive, this also known as no energy devices, whereas active known as active devices. In passive, we're gonna use passive due to the presence of a structure, the flow gets altered. Whereas in active flow control, they're gonna be a device, electromechanical device, which also known as energy source, external energy source, so which alters the flow. In our case, we're gonna consider synthetic jet. Synthetic jet. So what is you gonna ask me what is synthetic jet? So synthetic jet is nothing but synthetic jet actuator is a zero mass active flow control which creates low pressure zone due to the oscillations in between them. As a result, instead of getting flow separation, it gets stick. Why? Because it create low pressure. As we know that the flow will the air will flow from high pressure to low pressure. So due to this presence of low pressure zone, the air gets stick, avoids boundary layer separation. So in this case, this is gonna oscillate like this. As a result, it creates a low pressure zone. So instead of flow going separation like this, it gets stick towards it. Why? Because it act like a suction. As a result, instead of this, so instead of flow going like this, it gonna go like this. Why? Because due to the presence of this one, it gonna stick like this. And next, that's it. And next, and nextly, okay. And next, methodology. So in this, the previous slide is gonna be the literature review, which is the conclusion of what I understood and what I take from the papers, from the referred papers. That's it. And the methodology. So for the design of that, I use it Naka. I use Naka 2412 and I design in CATIA V5. So this is one which I designed in CATIA. So I designed the CATIA. And next, so for this, so I imported the Naka airfoil plotter. I imported the corners from Naka airfoil into the CATIA V5 with the chord length of 100 mm, and I generated 2D surface using CATIA V5. And next, methodology. So this is the actuator portion, and these dimensions of the actuator was considered using from the research paper, from the referred paper. So this was methodology. So this was the each individual step which I refer from the paper. I didn't take the I didn't choose a random number for the actuator. I just refer from the research paper. That's it. And for answers, so for each individual step, like how I did the analysis, I gonna attach a video link to this video which I gonna explain each and individual step, like how I did so it's nothing but an overview of how I did the analysis. That's it. So in simpler words, first I imported the a4 and then just design the domain and then just draw the two lines, and I split the surface, and I give the edge sizing for this one, and then I also do the face mesh for that, and then and here I give the bias factor. So you can see I give the bias factor, and for in the here I give very finer number of divisions. So that's all I got the structure mesh. This is a structure mesh. Yeah, so this is a close look of that. So these are some my mesh reasons. This is the domain dimension. This is gonna be my mesh reasons. So for simulation, I from research from the referred paper, I'm gonna consider Spartans, Stubbornness model, and I'm gonna use RANS model. Why? Because for this aerodynamic application, RANS is good in comparison with LES and DNS. So this gonna take a much more computational time rather than this. But the results were much similar. So for me, for this simulation, it took me 2 weeks. So what if I gonna use LEs and DNS, it's gonna take like 1 month of time. Why? Because these for these LEs and DNS, the NASA gonna use supercomputers to solve it. Where we as a students, we don't have supercomputers, so that's why this ranch is good. This is mesh independent study. So it's nothing but first we gonna create the mesh with n number of elements, then we increase the mesh, then we gonna see is there any difference between lift and drag. So up to a limit, so we gonna see the difference, and then beyond the limit, if we increase the mesh, the results gonna be same. So then we gonna say the limit as mesh independency results. So for me at 11 lakhs I gonna get these results, and then I ran the simulation for 13 lakhs elements, then I got the similar lift and drag. So that's why, so I just consider the 11 lakh elements in our case. Why? Because solving, like considering 11 lakhs and 13 lakhs gonna be same results. So if I consider 13 lakhs, it's gonna take more time in comparison with 11 lakhs. So we're gonna get same results. uh, why? Because we ran mesh independency. So this is the results from parametric analysis. I also explain how to do the parametric analysis in the video. And so in this I consider the y plus value. So y plus is nothing but the boundary layer, the height of a boundary layer of the airfoil edge to the first boundary layer, the first boundary layer of the flow. So why? Because for the airfoil, so it's nothing but, so this gonna be the airfoil. So if we consider this is the first layer, so then the height, this height, so the height between the edge of the airfoil to the first boundary layer is gonna be the y plus value. So we're gonna give y plus value this one. Why? Because this is the value. So if we're gonna give the y plus value like this, we're gonna form mesh in between this region too. So we're gonna form mesh like this in this region so that we can study more about this. So for the boundary layer kind of problems, we're gonna consider y plus value. Why? Because the total phenomena gonna occur in between the boundary layer, so that's why this height is much more important. So if we don't consider y plus value, you will give the first layer at zone here, so you can't able to get the results. So if you give the results, you give the first boundary layer of the mesh. In between these layers, you're gonna give 5 layers, then you're gonna capture it. So that's why consider this value is very much required. Next, so first I ran the simulation for plane airfoil, uh, and then I ran the simulation. So this is the results for plane airfoil, and then later I ran the. So this is the so so this is I ran the simulation for synthetic jet one blowing. So this is a results. This is a graph. So in comparison, so this one. So at angle of attack 18.66, we got boundary line separation at 0.25% of chord. Whereas we close the actuator at 25% of chord, we can see the flow got stick. Why? Because it created a low pressure region at the spot. As a result, instead of flow separation, it got stick and the flow is not separated. So as a result, the lift will be increased, the drag will be reduced. So in conclusion, I can say the placement of actuators is not a random number. It was referred from the research paper which they're gonna get by multiple studies. So in conclusion, the the so this is the results of plane airflow. The lift is gonna be 32, whereas if you're gonna use this, you're gonna get you're gonna get 274, which is more than 9 times increase in a lift. Whereas see for the maximum lift for the plane airfoil is 274, whereas for actuator we got 414, which is like around 50% of increase, 50% increase. Whereas the drag for the plane airfoil is 32, whereas the actuator case is 13.55. So in conclusion, so these gonna be very much useful if you are planning to study in much detail. You can go ahead. Why? Because I ran simulation for steady state. I also consider transient, but for transient gonna take more time, and my system is not capable of that. So I just ran the steady state. For me, it took 2.5 weeks, like 2 weeks to solve the simulation. If I choose the transient, it's gonna take 4 weeks. So if you are interested, or if you are looking forward to do transient, you can contact me in the comment section so I can reach you out, so we can work it out. Because if you have a very higher end computer, just text me, just let me know. If you are interested, we can work together, and we can work on it. That's it. Thank you. And I will also attach you one more video of like the go through the overview, like how to solve the simulation in the CFD. Gonna be individual steps, each individual steps which I did. That's it. Thank you.